All right. Everyone ready to start again?
Ready or not, here we go.
Yeah, here we go. We thought we'd just start back in our old slide and ask you all what these terms mean. So does someone want to start by telling us what epsilon is?
Dissipation.
What kind of dissipation? Wait, don't
No, please, by all means, I was joking. I could.
No jokes in this class.
I'm joking.
Come on.
Austin just leaves the ball in the sleeves.
Okay, transfer of kinetic energy to heat energy due to high viscosity.
And hi.
Come on, guys. Someone knows what chi is.
You got this.
You just talked about it.
It's like temperature variance of something, yeah. Forgot the actual term?
No, you don't have to know the exact terms. Just what does it mean?
Oh, okay, dissipation of temperature variance.
Yeah, basically, yeah. Perfect. Thank you.
Viscosity. This is
Just depressing.
Is the equation of momentum.
Sorry, repeat that?
The equation of momentum.
Yeah, it's it's related to how much things can diffuse, I guess. You had a better definition the other day, right?
Yeah, you did better.
Viscosity, yeah, so it depends on the kind of viscosity you're talking about. Because if it is mu, it is the rate of resistance of a fluid to like strain. Whereas this version is sort of like how the deformation of the fluid under gravity.
But it's related to that
Those
idea
are all
of how much it's how much the fluid is willing to be stretched, which is obviously related to, as you said, diffusion of momentum.
Thermal conductivity or molecular diffusivity, really. Molecular diffusivity might be a little bit more helpful.
I guess I would say like how quickly energy can move about within a given material. How much it can go from one source to spreading out to that source.
Yeah, I guess that's sort of the idea. Yeah, it's sort of at the molecular level how heat is being diffused. Eddy diffusivity.
I think that one is also related to momentum, like the velocity of the eddy, right?
Yeah, so it's the idea that turbulence kind of enhances mixing. So now you have, or we have in oceanography ways of kind of estimating that as a type of eddy diffusivity. Because really, I mean, diffusion happens at those molecular levels, like we just talked about, but this is a way of kind of getting an estimate of that.
And it happens for momentum, but it also happens for other quantities as well. It's the idea that you have, because of turbulence, you have an increased spreading. So you've increased your surface area by which you can have molecular diffusion. And so you wrap that all up in just one name, which is eddy diffusivity.
Right, and I talked about these yesterday in my lecture too, and we said that the thermal conductivity or molecular diffusion sort of, like there can be like 2, 3, 4 almost orders of magnitude between D and kappa, just in terms of size, because like Andrea said there, when you introduce the molecular diffusivity depends on what medium you're trying to push something through or diffuse something through. But when you go to the kappas, you add in like the properties of the flow itself. And like Andrea said, when you start moving things about, it's just easier for those gradients to be smoothed out just because you have more surface area and like smaller scales of things being moved sort of.
Yeah. And the final one is mixing coefficient, which is really a factor or one of the variables that goes into any diffusivity.
Point two. It's a matter of how efficient, like mixing exchange, like exchanges in buoyancy or in temperature. I don't know if the mixing side also for the temperature variance equation.
No, it really
It's just for
comes
the
into
buoyancy.
play. Yeah, it comes into play in buoyancy because you can it's just a way of simplifying that equation by defining a ratio between the production of turbulence through shear, which we talked about a little bit, and then its loss in kind of taking density to buoyancy. So, yeah.
The way that we've defined our like molecular diffusivity and eddy diffusivity, would the ratio of the eddy diffusivity over the molecular diffusivity be something like the ratio in area of the surface between, or like the interface before and then after mixing or stirring? Like it's, can you think of it as?
They're related to each other. Yeah, I mean, the reason why they get the same name, but just with eddy in front, is essentially because of what you just, it's because of that, like you've increased the surface area, and so now you have it's effective diffusivity. So it's like, and yeah, you can see it as either like, okay, well, the turbulence has created more surface area for them to interact, and therefore you just have a greater chance of having, or like it's easier to have more molecular diffusion. Or you can see it as like, okay, it's effective molecular diffusion. The problem is, again, like the problem with eddy diffusivity as a concept is that it's a property of the flow and not of the fluid, unlike molecular diffusion. And so that's why it gets a little weird to think about, because they're just fundamentally applied to two different, like one is related to the material itself, and the other one is related to the situation the material is in. But yes, that's why you could think of it as kind of like, if I were to like fold this over 1 million times and increase the surface area massively, how much would that increase net my molecular diffusion?
I guess you're asking from a like process perspective, because are you thinking that can you write kappa T as a type of like process that's changing temperature? Is that kind of, because you're talking about stirring, right?
Yeah.
What do you mean by stirring? Like
Just like stirring as like a process of increasing the area of a surface that is the interface between like two fluids, right? I'm just asking if you can fully describe the difference between the eddy diffusivity and molecular diffusivity as that change in geometry. Or if it's also talking about like, if you stretch this out, there's like velocity things, there's like, I don't know.
yeah, I have not seen a like comparison of the two, because this is really sort of an estimate, and it's like even a sort of
You would sort of need to quantify how much additional area the turbulent stirring managed to have. And that's really difficult because turbulence is kind of a fractal thing.
Yeah.
It's infinitely detailed, so it's hard to even think about like what surface area means in that context.
Exactly.
So it's a lot easier to just imagine it as a God-given whatever.
Well,
And that surface area too, like when we've drawn diagrams today, we've done like blue and red or like yellow and blue, and it's like a perfect line between the two. But when we actually zoom into the ocean, like it's not a here and here, it's like a gradient in between. So what does the surface area between those two actually mean when you start folding it up, and like where's the gradient kind of? So yeah, conceptually it's not wrong to think about that. Yeah, it has to do with how much more space do we give this thing to diffuse kind of thing. But yeah, it probably wouldn't be something that you could actually measure or like sample and fluid particle, like how much more surface area do we now create between X and Y with the diffuser.
yeah. I mean, you could definitely do it in a lab, but I think it would be very difficult to do it.
It would be very modeling kind of thing, but yeah. Right, like conceptually, you're on something, yeah.
Cool. So moving on, and I think this is you, Andrea, right? You're the
Yeah.
first one. Okay.
Great. So now we're gonna talk about the TKE spectrum a little bit, as well as some of the shear spectrum in a little bit as well. I kind of feel that Charlotte covered a lot of this information, so I don't think we have to spend too much time on this. Basically, before we were saying how we go from energy going into kind of the mean flow, and then it's getting slowed all the way down into like they're cascaded down into small scales, and then eventually at small enough scales, viscosity is relatively high compared to the scale of motion, and now you get viscous dissipation. We're all cool with that. I hope. So what you can look at is like if we kind of see this as the same kind of energy transfer in this diagram here, you can look at the spectrum of turbulent kinetic energy for each scale. So in the same way that we saw in the previous presentation, you have your wave number increasing to the right, which means your scales are getting smaller. And then this is your energy. So what Charlotte's plot was showing was looked a little different. Does anybody know? Can anybody guess why it was different? Yeah.
What I know is that the slopes were different.
Yes, it was different because of the slope. But do you have any idea of what the reasoning for why this slope is different from hers? Hers was 1/3 of the inertial subrange. Ours is -5/3. Exactly. She was looking at a different quantity. So, you know, it's easy to just be like, yeah, this is the spectrum for dissipation or whatever. But like, what does that mean? It depends on what you're plotting on the y-axis. So here we're plotting energy. What she was plotting was the shear. So we'll get into that more throughout this lecture to kind of disambiguate those terms. If you are looking at the shear across, or the energy across different wave numbers, in the inertial subrange, we have kind of done some scaling arguments, which I won't get into. Well, Kolmogorov did, I didn't do it, to figure out what the relationship is between energy and wave number. And what he got was that it's a constant times epsilon to the 2/3 times k to the -5/3 in this inertial subrange. It's obviously not that elsewhere. That's really important for the same reason that Charlotte was discussing earlier, which is essentially that you can kind of get an idea of what the process is that you're looking at depending on what these slopes are. Not always, there are other things that can give you a -5/3 slope. There are other things that can give you a +1/3 slope, but it is a good indication that what you're looking at is some kind of turbulent process. And what you'll also notice is that in this case, this -5/3 is referring to K. It's not anything to do with epsilon. So that's something that confuses people as well, because you're like, epsilon's a rate. So the slope must have to do with epsilon. We're plotting it in terms of wave number, and epsilon is like a rate of turbulent kinetic energy dissipation per density. So it's not even showing up on this plot except as like a level. So kind of like when Charlotte was showing the different epsilon layers, and it just made this the same spectrum kind of go up and down. It's the same thing here. So for the purposes of this spectrum, epsilon is just kind of like the magnitude you start at, and then everything else, or you start at, I guess, here, and then everything else is dependent on this K. And obviously it looks different in frequency space than in wave number space, but for most of our work looking at turbulence, you tend to look at things in the wave number space. Does that make sense to everybody? Yeah. No? Yes. Okay. And then another thing to think about is kind of what is this representing? This is not showing you like a process, I guess. Like it looks like a slide, and we've talked about downward energy cascades, and it's like, oh yeah, this is going to this, is going to that. And like, yeah, that's happening kind of in the background, but you can kind of see this almost as like an instantaneous look at what things look like in that, like how much energy is at different scales. So it's not necessarily telling you specifically in this plot, like how much energy is going from here to here to here. It's just saying how much energy is located in this scale, and how much energy is located at this scale, and how much energy is located at that scale. So that's another important thing to think about, is just like, what is it actually telling you? It's just giving you the distribution of energy across scales. And that slope is related to K and only 20 kN situation. Here we have our energy increasing because at small scales, or sorry, larger scales, you have input of energy into the ocean, so tides, wind, etc. And then we have our inertial subrange, and then we've also got these two lines, which will be explained in a moment. But basically, what you can see here is that there's clearly places where the behavior changes. And so when I say that this only applies in the inertial subrange, I'm saying it applies between these two numbers that Charlotte mentioned, but I don't know if any of you remember, and that we are going to go over now. But there's different behavior outside of that range, though for dissipation, there's
I have
yes.
a question about what you said, that this is like an instantaneous distribution of like energy across all scales.
Yeah.
Because otherwise, how do we know, for example, Charlotte was showing how you can compute, like, if you do like a low pass filter, for example, you can look at like where how energy is transferring from one scale to like another one. But if this is like an instantaneous shot, like of what is happening.
Yeah.
How can you know like this transfer of energy is gonna happen?
Well, so I think Charlotte plotted it in frequency, right? as well?
What was the question again?
She was asking, I was saying, like, you know, if you look at this and this is just telling you how energy is distributed in scales. She was asking how you make your plot that like had the arrows showing the transfer of energy.
So you can actually tell from a spectrum how energy is transferred between scales. It is just a snapshot of how much energy is in those scales at that time. It's actually pretty hard to compute the energy transfer between scales, and that's where all the like fancy force graining and structure functions come in.
So,
Yeah,
so that's what,
yeah.
like, it's
Yeah.
confusing. That's why I bring it up. Because it's weird to think about, and it wasn't frequency, which why it also looked completely different. But like what Charlotte did a lot of work to make that plot. And so basically that's what I'm saying. Like it can be a little confusing when you look at the spectrum, and I think a lot of us go like, oh, slidey, this is how much things move. No, this is just like how much energy is at these scales done. And then because you say like, oh well, epsilon, you know, if we assume that energy is transferred like at the same rate across everything, then why is like how can epsilon, which is like measured around here, going from the inertial subrange to like viscous dissipation range, why is that the same as this? These are different numbers. And it's like, no, one of them is looking at how things transfer across scales. This is just looking at what the scales have in that moment. Okay, yeah. Thank you for the question. It was exactly what I wanted to hear. Anybody else? No? Okay. Great. We're going to talk about those numbers now that I deliberately omitted. Well, Helen does some acrobatics.
Hi, guys. Cool. Well, thank you for that intro. So these are just the two lines that are on either end of the energy spectrum that we were just looking at. So on the small side, we have the Osmodov scale, and that is the size of the largest eddies. Basic. What?
Small side.
I get small and big mixed up all the time with the wave numbers. Sorry. The biggest spatial scales and smallest wave numbers that you get comes from the Osmodov scale, which is governed by the ratio of the amount of energy dissipation, epsilon, with the buoyancy. So if you kind of think of epsilon as like the injection of kinetic energy, then the buoyancy is sort of the amount of potential energy that you need to actually overcome in order to get that overturn to happen. So yeah, that sets the largest size an eddy can possibly be. That's cool. Oh, this is just pointing out where it is. Yes, the smallest wave number. So here are some typical numbers for what this line scale would be in the ocean. Quick math. What would roughly be the order of magnitude for the Osmodov scale? It's just arithmetic.
Oh, square root 10.
Right. Yeah, so we have, let's see, what do we have?
I did the math for the next line.
Well, yes, I know, but
Oh, okay.
yeah. So you actually get something on order of one. And I think so if you have 10 to the minus 4 times 3. So, yes, okay, cool. So you have 10 to the minus 6 on top, and then you have 10 to the minus 12 on the bottom, because it's n cubed. And then you have 1/2.
Square root 10 to the minus 2 times 3. It's and square root of 10 to the power of minus 4.
I'm getting to the square root.
Oh, because it would be 10 to the power of minus 6, not 12. Since
Just because the
And
form factor.
Squared, got it. Yes, okay, cool. 10 to the minus 6 over 10 to the minus 6. Oh my God. I'm sorry, I did this out earlier, I promise. So yeah, so you have 1, and then you have the square root of 1, and you get 1. Great. But this depends on where in the ocean you are looking at. If you are somewhere with a higher mixing efficiency, you might have a bigger number. If you are somewhere with a very low stratification, like maybe along the bottom of the ocean, you will get a bigger number. And if you are in the thermocline where the stratification is huge, then you will get a much smaller number. Make sense? Cool. Awesome. Yes.
Wait, so that length though is like, that's the radius or of the eddy, like,
It's the inverse of the wave number. So it's a wavelength.
it's the wavelength of, okay.
Yeah. Yeah. Good clarification. Anything else? Okay, great. All right, so we just talked about the biggest, and now conversely, we have the smallest possible eddy. And that is governed by the Kolmogorov scale. So this comes from a scaling argument that Andrea alluded to earlier, where if you make the assumption that as turbulence gets bigger and bigger and your length scales get smaller and smaller, the only thing that length scale could depend on is the mixing, the energy dissipation rate and the viscosity. So this is the scale past which, if you are smaller than this, viscosity takes over and you are just generating heat. That is here, smallest. What? Questions? Yes.
Wait, sorry, this is a vertical length scale?
Are these waves in the vertical or in the horizontal? They're in the vertical.
Assuming that it's isotropic, so it's all. Yeah, it's.
You don't need to assume. That's
I
a
just would assume
In the
myself.
inertial sub-range, you assume myself.
Yeah, it would be assuming.
Okay.
So I don't think.
So yes, we do.
Or are you assuming local isotope? I guess it generally you where you say wave number and then you're looking at like measurements, it's usually vertical wave number. I think in this situation, the idea is that it could be kind of neat almost because if it's isotropic, it would be the inertial subrange, and that's really the only thing that's on this plot right now.
The other thing is both energy and viscosity are scalar quantities that don't have direction. And this scale is just dependent on scalar properties. So kind of it is isotropic. That's the definition.
I'm just confused about the inclusion of the buoyancy or something that's isotropic,
Yeah, buoyancy is the previous one.
or not buoyancy, sorry, the Raphael. In the other one.
Yeah, in the other one. For the other one,
That's where isotropy is starting.
yeah, if you have a eddy that's going everywhere and including in the vertical, it still needs to be overcoming that vertical potential energy. Like a spring, you need to push on it hard enough to get it to.
So the strongest barrier to turbulence would be the vertical gradient and or the
Large scales.
large scales. And so that's isotropic.
Yeah, whereas these, the strongest limiting factor on the smallest scale is molecular diffusivity. Or actually not molecular diffusivity, the other one. Any more questions? Okay, thank you for clarifying. All right, let's do this again. See if I can do it better this time. Here are some typical numbers. What would this scale be? Yeah. Yeah, good job, guys.
Great guess.
Yeah, yes, I was trying my advanced teaching method where I mess up and then you guys learn what not to do and then you do it perfectly. Good job. Yeah, exactly. That's right. But once again, there is a whole range of possible values in the ocean. So this is a paper that put a bunch of different, this is state space actually, of the amount of buoyancy versus epsilon. And here, because these diagonal lines are the Osmondov scale, it's just buoyancy. It's just epsilon over n scaled by different things, so it comes out as a diagonal. And then we are also kind of assuming that viscosity is constant, which is a good enough assumption. So your tidal channels would have like a larger maximum possible eddies, just because the dissipation rate is so high, not because it is unstratified. On the other hand, you can also have like a pretty low dissipation, but with lower incident, you can also get a larger overturn. Yeah, and same as that. Basically, the point is, it's all over the place, but it's governed by these pretty simple quantities. Okay, cool. And with that, we're going to get into what is wrong with everything I just said, because that's actually not the end of it if you are talking about a scalar.
Yeah, so what we talked about so far is the spectrum on the top, which is for turbulent kinetic energy, and you get that sort of familiar homograph slope of -5/3. So in the case of temperature, and that's the kind of scalar we're thinking about here, over that, there's a additional kind of subrange. So you start out with that inertial subrange, so you have that -5/3 slope, and then you hit the chronograph scale. So as you remember, the chronograph scale tells you the length scales at viscosity becomes important. And once you hit that scale, any viscous driven processes are sort of dissipated as into molecular heat, but you still have continued temperature gradients that are created. And that can drive an additional kind of subrange, a viscous convective subrange. So you still have the sort of stretching and straining of temperature gradients, even though the kind of momentum variance has sort of been dissipated away. And that still drives additional diffusion of, in this case, heat. But you can also kind of smoothen out gradients and salinity as well, and this kind of idea holds. And that was why your slope changes to a smaller slope. So now you get a -1 slope. And then eventually you get to a scale known as the Bachelor scale. That's when you also are diffusing heat. And that is the sort of viscous diffusive scale.
Wait, sorry.
Yes.
Can we look at what is the difference between E and E naught?
Yeah, so E naught is a spectrum for temperature variance. So now instead of looking at turbulent kinetic energy, we're looking at temperature variance instead.
Okay, so capital E is the T phase.
Yes.
Oh, okay.
Yeah.
It really shouldn't be called E, I feel like it should be like E naught, you know?
Yeah, it shouldn't,
Yeah.
it's a notational thing, but yeah, it's just showing the difference between what you'd expect to see if you were to like plot the gradient of or temperature fluctuations in this case versus velocity fluctuations. But does that difference makes sense of why you would expect to see. And we'll look at the actual numbers, just kind of like Helen did. We'll look at the numbers a little bit as well, just and that should hopefully help see why they're so different. Yeah, so that scale at which molecular diffusion of heat becomes important is known as the Bachelor scale. And that's the equation up there. So remember epsilon, we just talked about that. You know what viscosity is, and D is the molecular conductivity of heat for a fluid. All of these are for fluid. So here, hopefully you can start seeing the reason why there's the scale separation for temperature. So Helen just talked about viscosity, which is an order of 10 to the power of -6. Now, if you think of the conductivity of temperature, that's about 10 to the power of -7, and salinity is 2 orders of magnitude smaller. And so all of these processes are sort of driving this molecular diffusivity, but at very different scales. So this is a bit of a trickier math problem, but somebody want to take a crack at what it would be for temperature? What scales would you expect? And here, just to note, the Bachelor scales that tend to be given as wave numbers. I have just taken an inverse of that, but really a wave number, you kind of need to multiply by 2 pi. So if you're actually doing the math out, make sure to include a 2 pi, but this is just an example for you all to get a sense of the scalings. Somebody want to try and guess what the scale for temperature would be? I'm also not going to try and do the math because that's very confusing, but let's see. 10 to the power of -6. So it would be 10 to the power of -4. So hopefully people see that really the kind of epsilon and viscosity cancel out. So it really is sort of 10 to the power of -14/4. Which I cannot do in my head, but thank you. But yeah, it's about 10 to the power of -4. And then if you think about that for salt, it's 10 to the power of -5. So as you can imagine, if you're trying to measure these, you really need a really precise instrument to measure fluctuations in salinity, just because of the scales at which this diffusivity happens. Does that make sense? Yeah, and then this is just a few examples from the ocean. Here the plot with the uncolored circles, the bottom one, it's showing you the energy spectra, wave number, against wave number, and the top plot is showing you the same for temperature, and you can kind of see they both have that -5/3 slope, and then it drops off. And then in the case of temperature, you have a shift up to a -1 slope, and it drops off. So that you see that in measurements as well. And this is something Andrea was talking about. So in the case of this shear, and Andrea, please correct me because I know you worked on this yesterday, but when you are thinking of shear, This is the equation that we kind of start with. And is that right?
Where are you trying to derive this from?
This is your,
Oh, yeah,
I thought I had it. Good, okay.
These are from the general one, that's be dy dxj. Okay, are you doing the whole derivation or just explain?
No, just trying to
The case
explain
squared.
I'm sorry, guys, this was a confusing point for us.
You trying to explain the case squared part of it?
Uh,
Part of the derivation?
Just how we got to K squared.
Yeah, well,
That was a bit confusing.
it's all in the notes and I can
Okay.
do it out like properly if you want after, but basically it's related to the fact that if you have a Fourier transform of something, and again, we can go into the details if you want, but if I have some u of x or something, and in Fourier space, we'll call that like u hat of k or something. Because to turn it into a Fourier space, you multiply it by e to the minus I kx. If you take du dx, that's then gonna be ik times u hat of k. Is everybody familiar with that? So we can go over all of the math behind this in a bit, but basically because of the relationship that we know that like ui is the integral of some e of k dk. Some like we can define this is our TKE energy, which we defined at the very beginning. If you Fourier transformed this E and then you took like the integral over all k, that gives you the same thing again. And so if you go through all of the math, which we can do, it's a little annoying, but if we have time, we can go over it. Basically, when you take the derivative of it, to get your dui dxj dui dxj, you end up with a situation where you have a k squared multiplying your e of k because of the fact that you're doing a derivative, and so you get some extra ik's in there. And then to get epsilon, you have to multiply that by nu, and there's also a 2 that comes out of this whole math, which again we can go over, or it's in the notes. So that's how you end up with that equation. Is by relating your original energy to the fact that when you take the derivative, you end up with some extra k's in there. And then a factor of 2 shows up as well because of various different pieces that we can discuss.
But each of those derivatives brings down one k from that e to the ik whatever. So because we're doing it twice, we have ik and then we have a minus ik because one of those is a complex conjugate. And then that's why you have 1 times k squared.
Yeah, that again, I don't want to go into the details right now, but the point is that when you take a derivative, you get a k squared.
Okay, yes. Yeah, we all got a bit confused about this when we were reviewing our notes yesterday. So thank you, Andrea. But yeah, so you can go from a velocity fluctuation to thinking of it in terms of shear, which is sort of plots that Charlotte showed. And that's the kind of stuff that you will see. And so this is an example of a plot from Arnaud, who will be teaching some of our classes. This is on DFC, the epsilometer or the microstructure profiler that the math lab uses. It's called Turbulence. And as you can kind of see, as they helpfully pointed out there, this profiler measures at a much higher resolution than we typically see for most CDCs or CTEs. And you can kind of see from what we showed here that your minus 5/3 slope, when you think of it in shear space, then it becomes a 1/3 slope. And
Do you understand where the 1/3 came from? what's -5, what's k to the -5/3 times k squared
Yeah,
is k to the 1/3. That's literally it.
and as a result, we can kind of see a familiar k to the 1/3 slope, and then these are theoretical spectra, and then the light lines are our actual measurements. And like Charlotte showed in her presentation, it's a kind of common technique to kind of test our epsilon measurements to compare it with theoretical spectra, and this is by just taking a bunch of epsilon measurements, spinning it by their values, and then looking at it with respect to what we would expect of the slopes. And so tend to show fairly good agreement.
Sorry, this
Yeah.
might be a minor detail, but is phi squared like what is phi squared in this equation?
Phi squared is the it is the shear. So
Oh,
that's
okay.
our measured at du dz.
Yeah.
So that's going back to Andrea's. See, I will not go back that far, but it's this.
We might have time to just do out the math.
I feel like maybe it is doing, just so we're not just. I might have messed up the math here, I'm sorry, but this is where that's.
Okay.
Yeah, but this is, we'll talk about this a bit more, but this, is making that assumption. Because we really don't, we don't have enough data. Sometimes we do, in this case we do, but in many cases, the measurements that we're really getting are of the inertial subrange. And we don't have measurements right up to the viscous roll-off, which is sort of this past the 1/3 slope. And so you generally assume, like Andrea said, that the energy that comes in in the kind of low wave numbers, we kind of integrate over that slope, and that's sort of the energy we assume is dissipated. So that's sort of, in a kind of intuitive sense, why we think of dissipation as a sort of integral of the shear spectra. If that helps, if you are not as math inclined. But yeah, that rests on that assumption that what's produced at these low wave numbers is then what's dissipated. And that's an important assumption in this scenario. And then finally, like I said, salinity is a bit of a tricky quantity to measure at these very small scales, but there's been some attempts to do that. But first, let's kind of compare shear and temperature. So as you can see, we have that minus 5/3 slope again. Sorry, 1/3 slope. We can see that same with temperature, but it rolls off at a much higher scale. And then some people have tried to do this by getting conductivity measurements, so that both is a measure of temperature and salinity, and you can kind of get and generally when you measure salinity in the ocean, you are sort of backing out from a measurement of conductivity what salinity would be, as you knowing that we also are measuring temperature. And so some very clever people have been able to do that using conductivity sensors to back out measurements of salinity. But that really kind of rests on the assumption that salinity is primarily driving conductivity. But when you do that, you can also extend your measurements and kind of see where the salinity drop-off happens, which is at much lower or much higher wave numbers, so much smaller scales. So it's sort of a proof of concept of things we've been discussing in terms of like bachelor scales and things like that. That's the kind of conclusion of our 2 lectures here. It's just kind of going over some of the first kind of teaser for things we'll talk about a lot. So these kind of concepts of, you know, what the the theoretical spectra looks like, what we expect from measurements. These are kind of things that we'll see a lot. So if you're confused about any aspect of this, do let us know. We're happy to explain it in a bit more detail. I'll leave this here for people, if anyone has questions. Yes.
Is there any benefit to? So I mean, we find epsilon high values by the geos spectra to spectrum here. Why do we well, when do you decide to use the shear spectra versus the scalar spectra with the energy spectra? When do you decide? It should be.
I think in our lab, we're measuring the shear, right, with our shear probes that like go down, so we're gonna use the shear spectrum because that's like what we have. Because
I mean, we also do temperature fluctuations too. So
Oh, I mean, sorry, I was saying like specifically for like the idea of like, why would you use like the 1/3 slope exam rather than like, I guess, trying to use the UK one, and the reason like why not -5/3? And it really, I think in a lot of ways, just depends on what you have and what you're gonna compare it to. If you're talking about like how you pick what's good and bad error, that's Nicole and Arno's problem, and so they'll explain it to you. But yeah, my understanding is that like because we designed a machine to basically measure wiggles as it goes down in Z, you're getting your dz, and so we have conveniently have the derivation of what that should look like in spectral form. So we just compare it to that spectrum.
Yeah, my project right now, I'm working with just the thermostats.
Yeah.
So I don't have shear, or but I compute in the horizontal and use that spectrum. I've been wondering for a long time why I'm taking that step, because it seems to me that I should just use my app, which is temperature data over time. But instead it's like, and so I was just wondering if there's a reason why we're taking it's just like better.
I feel like I think it usually just depends on what you have. I mean, I don't know why in your specific case, you might be doing that. Might have to do better. Maybe there's less error in taking the derivative than not. That seems unusual since usually it's the opposite, but maybe it's also because something to do with like the temperature variance versus the temperature, because unlike with like shear and energy and all that stuff, it's all assuming like variant velocity. I don't know what you have in terms of your temperature data, but that's more.
Do you correct it with, like, are you using a bachelor spectrum fit to get your measurements? That's probably why, because I think the bachelor spectrum is the what is it called? Like the form of the equation is based on your temperature, dt dz, isn't it, or whatever gradients?
It's based on.
Yeah, I think that's probably why. I guess in theory you could use just temperature fluctuations. It might also be, this might be a question to bring up with Arno and Nicole, but I suspect it might also be because when you have a profiler, you are kind of deploying the profiler, it's falling, free falling, and so you're getting like a fall rate that you use to correct your measurements, and so are kind of you're measuring in time, and then you use that fall rate to get a measurement in wave number, and I think it's probably why it may be easier to do gradient versus temperature fluctuation. But yeah, it's a good question. I'm not sure. It seems like a analysis thing. Any other questions?
Now's your chance, guys. We got us on the clock for the next 5 minutes. We have to answer your questions.
And again, we will see this come up in many different ways. You'll actually get to see what it looks like and measure it. And so hopefully, if you're feeling really confused right now, hopefully it'll start making more sense as you start looking at data and
I also really strongly do recommend looking at the lecture notes.
Yeah.
Cause there's a lot more detail in how you get from one step to another. Like we wrote out the entirety of like how we went from the turbulent, Navier-Stokes part to the TKE equation, and then how you get from like the relationship between the, string tensor notation and the epsilon notation we've been using here. We explained where the, like, how you derive the K, like the shear spectrum is equal to K squared times the E of K spectrum. And again, all of those things aren't like critical to know. It's just nice to have, because that way when you have random floating 15s or whatever, then it makes a little more sense where these things are coming from. And a lot of the time it's coming from the fact that like theory says energy is this, we only have one component to measure this with, so we use isotropy and assume relationships, and that's how we get a lot of these things. So a lot of the stuff that we do in oceanography is playing a little bit with the theory to figure out what we can actually measure, and then hoping and crossing our fingers that everything else satisfies the assumptions that have to be true for you to make that that jump.
And I will say, sorry, just going back to the Kai thing, the other thing that your method probably does is the bachelor spectrum assumes that the production of turbulence is shear driven. And so you don't actually see this part of it in the spectrum. I think that's my understanding as well. Please correct me if I'm wrong. So you're kind of assuming in your calculation that all of the production of turbulence is shear driven, which good or bad, I don't know. you will find out. But, yeah. If no one has questions, guess we can take a break and we'll meet again for IK's session on computing Richardson number. And I guess while we're on break, if anyone has problems with setting up Python, this might be a time to troubleshoot. I'm happy to help with that as well. And for people on